Okay, I think we're finally recording. And it's a exercise against Alzheimer's every day to get this whole system working. It's an unbelievable number of steps. And I don't think anybody who is sane would do what I'm doing. But then we never, at this university, guaranteed that the professors would be sane, did we? So there you are. We are at Lecture 7, and here's where we've been, which gives you a sense of what's going on. You should have read Chapter 11, or I should say really Section 11.1 in the book, and I guess your homework was due. You have a new homework, actually. Let me fix this. This is not updated. This is homework 3 is now posted, and it's due on the 22nd at 11:45. So basically, you're kind of, hopefully at this point, getting the pattern that we're going to have a homework due every Tuesday up until the midterm. And the midterm, I believe, is the last Thursday in October. And we will have a homework due that week. That means 2 days later we have a midterm. And I'll open up an extra couple of office hours on Wednesday if people want to come by. Also on Tuesday I had my office hours and I opened the Canvas conference system, but nobody attended except our TA, John Soup, who appeared for just 1 second and then vanished. So I don't know what you were doing, but I did see your name there for a second. But if anybody wants to try it out, I'm sitting there in my office waiting for people to join, or you can come by in person if you want. But if you want to avoid walking, because we're getting so much walking coming to this class every day, you can always join via Canvas. There will be a couple of points when I'm traveling this quarter, and we'll have only YouTube lectures, but I will have office hours via the Canvas system. So I suggest that actually next time, maybe next Tuesday, even if you just want to try it out, if you don't have a question, and you can just say, hi, I'm just trying out Canvas, and I'm stopping by your office hours virtually just to see if this is even feasible. Because at some point, you might actually need it, but at the time you need it, it might be like, the day before the midterm, and maybe at that point you realize that there are technical problems that you could have debugged when you weren't under duress. So hopefully you can try that out. So I invite you all on Tuesday to try it out. So that's this point. Actually, let me ask a question. Did anybody get an email announcement saying that I had opened up the conference? Yeah. There we did. Okay, so you guys got email. It seems like everything I do there, you guys get an email. So that's good. And you got an email, and you get an email when I post the YouTube videos? Yes. And you get an email when I post the homeworks? Okay, so that I don't have to send an additional email. All right, good. Okay, so as a review, so by the way, if you haven't noticed, we have every day in lecture we have this review section up here. So it shows you where we are in the lecture. Every single slide, for the most part, actually so far this quarter it's been the case, every single slide in this review section comes from a previous lecture. And so all of the new slides, all of the previous slides that you haven't seen, or at least that we haven't yet talked about, are after the review. So all of this stuff is stuff that really is review. It's no kidding. A couple of times what I might do, and I haven't yet done that, is sort of do a summary slide, an additional summary slide that occurs just in the review section. But for the most part, it's meant to really be exactly what we've seen before. And this particular slide is no exception. Remember what a type is, right? A type is a histogram. We've got a sequence of length n. We can compute the empirical histogram, which is basically the normalized count of how many times each symbol occurred. And there's some number of types, and script Pn is the set of possible types. The type class is this notation, and if we union together all type classes, we get the set of all sequences. And so this ball here, this oval, I guess, ellipse, is meant to be all possible sequences, and that set of exponential number of sequences are partitioned into type classes, and so each square, or square-like shape, corresponds to a type class. Right. And then one dot in there is a particular sequence. And so, of course, what this means is that there are some, all of these sequences corresponding to all of these dots have exactly the same type, which means they have the same number of sequences, same number of symbols in that sequence, and of course the same number of different sort of tokens of symbols, but they're just permutations of each other. So script Pn is the set of all types. I think that I've done this. So we had a couple of theorems that we proved, which was this upper bound on the number of types, which was polynomial in n. And that's the critical point again. It's polynomial in n number of types. Number two, using the language that they use in the book, which is, it's loose language, but you should be wary of that language. It's basically saying that the probability depends only on the type. And what we really mean by that is this. It's this bit here. That if we've got the sequence, actually let me use a more visible color, like yellow. If we've got the sequence x, its probability is based only on its type, and its probability is given exactly, it's an equal sign here, is exactly by 2 to the negative nh, and it's the entropy of the type, with, in some sense, some penalty, which is how far away the type of that sequence is from the true governing distribution. And so therefore, we should expect that, on the one hand, the trivial assumption is that sequences that have types close to Q are more probable, but more importantly, those sequences, when n gets big, only those sequences that occur are going to be the ones that are very, very close to the true distribution. Okay, and so we're going to get to n to the negative nh, just like we saw in AEP. We had this little lemma, which basically says that under a given type, being the generative distribution, so this theorem is saying, assuming that P is the generative distribution for a given set of sequences, what type is most probable? So that's basically saying, well, the type itself is most probable. Meaning, when you say by what does it mean what does it mean to say that a type has a probability? What we really mean is the type class of that type. So, and the type class basically means all of those sequences that correspond to that type, or all of those sequences that have that particular type as its type. That type class is the most probable type class when the true distribution is that type. I hope that made sense. But it's actually, that's correct. All other types, namely p hat, can never be bigger. We had this nice little bound on the size of a type class, an upper bound, which is, well, how big is the type class? Well, it's no bigger than 2 to the negative nh, and it's no smaller than 2 to the negative nh adjusted with a polynomial divisor, polynomial in n divisor. So nice upper and lower bounds. So basically, you can think of it up to essentially the exponent. The type class scales as 2 to the n times the entropy. So you can kind of, maybe if you were sort of well-versed in the asymptotic equitation property, we can see, okay, well, this is now getting to be the case that if only one type occurs, namely that type which is closest to Q, it's only going to take nh bits to code for that. So basic theorems, again, it's the same thing. So polynomial number of types, probability depends on the type. The size of the type is up to the first order of the exponent to the negative nh. And the probability of a type class, I don't think I restated this one, but the probability of the type class here, maybe that's actually this theorem. No, I didn't restate that one. But the probability of a type class is given by 2 to the negative n times the color level divergence between p and q. So this is under q. Up to, again, the first order of the exponent. Okay, so we're going to use these things. So hopefully, let me just pause for a minute and let you internalize them, because we're just going to use them. And when I give you a bound, it's going to be because of one of these things. So if you're confused about how I derived a step, come back to this table. The last definition we did before we stopped last time was a new notion, although it's a very similar notion of a typical sequence. And the typical sequence, it's going to be a function of epsilon again. Let's just zoom in on this a little bit so you can see it in big letters. The typical sequence is a function of epsilon, And it's basically all sequences who are epsilon close in the KL divergence sense to the true distribution, namely sequences whose type is epsilon close in the KL divergence sense to Q, which is all this stuff here. Okay, any questions on this? There's also, all this other discussion stuff we had here. We talked about that last time. So how do you like the method of types so far? It's pretty typey, isn't it? It's like a typewriter. No, that doesn't make any sense. But then I never said anything I would say in this class would make any sense. Maybe saying it's like a typewriter makes as much sense as these theorems. Is that correct? No, it's not correct. Good. Right answer. So, okay, so let's look at this theorem. And what this theorem is saying, well, in some sense it's a direct consequence. We're going to prove it, but it's basically saying the opposite of what the previous thing is, which is that the atypical sequences, the complement of the typical sequences, which are, let's just write it down. So this is the notation of the complement, and these are the sequences who are not epsilon close, but are epsilon far away. So notice that the inequality is pointing in a different direction here. Okay. So the previous case it was less than or equal to, now it's greater than epsilon. So these are the atypical sequences, it's a complement. But what it's saying is that something very interesting and powerful. It's saying that is bounded above by this decaying in n exponential. So epsilon is a non-negative number, a positive number, and minus x log n plus 1 over n. So we've got a numerator which is growing as log n, and a denominator which is growing as n, and the alphabet size is fine. So eventually that guy's going to get small, and that whole thing's going to be positive when n gets big enough. So at some point that's going to be a shrinking exponential with n big enough. Because eventually, if that doesn't make sense, eventually this thing ultimately is going to be greater than 0, ultimately. All right. And so as a consequence then, we've got this bit, which says that, this is a random variable. But let's zoom in on this so this makes sense. So Q here is a probability distribution. D is the Kullback-Leibler divergence. And P is the type of this random sequence. So it's a capital X. So it's a set of random variables, a set of n random variables, or a sequence of n random variables. And so the type, it's a function of a set of random variables, and so therefore it is a random histogram. And so this whole quantity here, this whole quantity is itself a random variable. And so we can talk about convergence in probability. And we're saying a convergence in probability to 0. And what does that mean? It means for all epsilon, there's just a delta and n, such that for all n greater than n 0, it's basically the case that we can make this thing as small as we want for any epsilon and any delta. Or the probability of that guy diverging from 0 more than by epsilon is bounded above by 1 minus delta for some all n greater than some n naught for any epsilon and any delta. That's convergence in probability.
Does the P or arrow mean the convergence in probability?
Yeah. So the question was, what is this little p doing here? We're sort of abusing p. Let's give it a little bit of nice green, friendly color. So that p means it's convergence in probability. So remember, I think it was 2 or 3 lectures ago, there was a set of slides on convergence, modes of convergence. I didn't actually cover them in class, but I suggested everybody go over them. Those slides are still there. Do go over them, and they talk about these different modes of convergence. And so in general, when you have an arrow with a little p of it, it means that it converges in probability, which again means that for all epsilon, for all delta greater than 0, there exists an n naught such that n greater than n naught is such that the probability of the difference between these two things, in this case, it's the Kullback-Leibler divergence of the 0, the absolute value of the difference being greater than epsilon, is going to be less than 1 minus delta for all n greater than n naught. That's all it means. So intuitively, however, it means that types that are really close at least epsilon close to q are going to be getting really small in their chance. So it basically means those sequences that don't have that type aren't going to happen. And the typical set is essentially, the typical set in our new sense of typical set. Remember what is typical? It's this. So here's the typical set, 7.39. The typical set is going to be the one thing that really only occurs without this sort of vanishingly small probability. So first, how do we prove this? So we're going to prove 7.1. So we start with the probability of the atypical set, which is 1 minus the probability of the typical set, which is the sum over all types that are atypical of the probability of that type class. This is the sum over all types that are atypical. And this is the type class. By the way, do you guys like this zooming stuff? Is this useful? Some people have told me in the past they like it. Some people find it distracting. But I think it zooms in literally on what we're trying to talk about. But on the other hand, if you're like looking at this equation on the left and suddenly it's gone, that's a little disconcerting. But I mean, I don't know. If you hate it, then I don't know. Don't tell me. No, actually, I'm kidding. Please tell me. So anyway, getting back to what we're trying to talk about. So we're summing over all the types that are atypical of the probability of the type class. And now what we're doing is upper bounding using one of those things that I said we should be able to refer back to, using the upper bound on the probability of the type class. And now this next bit is saying, well, okay, so we're summing over all terms where the KL divergence is greater than epsilon. So therefore, epsilon is less than the KL divergence here. So if I put epsilon in there, I'm only going to increase 2 to the n, right? Because it's a negative. It's a negative in the exponent. So therefore, I've grown that even further. But now, in some sense, the summand, the things we're summing over are such that we can, again, divorce the index from the thing we're summing over. And now we can just do counting. And we're going to do our upper bound counting. And again, any polynomial will work. And we have this, very loose upper bound on the number of types, but that's okay because we're hitting it by an exponential. And then the last stage is just sort of writing it in a different way. It's taking 2 to the log of the polynomial and then putting it up in the exponent, and we get this quantity here. And so therefore, like I said, eventually the exponent, the thing in the parentheses, this thing is going to go positive, and so that whole thing is going to be a negative, growing negative. It's going to be decreasing the whole sequence, and so therefore the probability, the right-hand side, is going to go to 0. So the probability of the typical set, since the atypical set goes to 0 in probability, the typical set has to go to 1. And this basically means the following. So this that everything, because the typical set is everything that happens, and so it's going to go to 0 with probability 1. KL divergence, that is. So this is just a little bit more stuff. But basically, let's compare this to the AEP. In the AEP, we said that it was the typical set, which is defined how? Does anybody remember? So now, in the current case, the typical set is defined as those sequences who are epsilon close, whose type class is epsilon close to the true distribution. Right. In the old case, it was basically said all sequences whose sort of, in some sense, average log probability is equal to the entropy, or epsilon close to the entropy. So we're being a little bit more specific here. So it doesn't really gain us in terms of coding guarantees because we showed that there was no smaller set that has all the probability that you can get more than nh bits. But what it does do in this particular case is it eliminates that case when we have a fair coin and we flip the coin 1,000 times and we see only 500, typically only 500 out of the 1,000 tosses will be 1. even though all sequences are typical, those ones that don't have a balanced number of ones and zeros are not typical in this new sense. So they're not going to occur. So in some sense, the other typical set is a little bit bigger than need be. But on the other hand, asymptotically, this is not saving us any more bits, but it's being a little bit more refined. So remember the picture of the binomial? This is what answers that question. Finally. Okay, so I said this already. Another way of looking at this is, this is an exponentially decreasing sequence, right? So therefore, it's summable, and it sums to a finite value. So here's the summation of this exponentially decreasing sequence. Here's the saying that it's finite. And then we can say, well, a probability is equal to the expected value of an indicator. So probability of an event is equal to the expected value of the indicator of an event. So this is like the expected number of times it occurs out of an infinite number of times over n. And so another way of looking at this is to say that the expected number of times that the event that were atypical out of over n occurs is finite out of an infinite set of possible times. And the Borel-Cantelli lemma basically says, as a result of that, says that this event must have probability 0. So the event that, and if anyone doesn't familiar with this book, this is a probability measure book. This is a classic book on sort of Lebesgue precise probability theory. And a lot of people who work on probability theory start from Billingsley. So I would suggest everybody take a look at that book if you haven't already, or you should probably own that book, actually. It's a really well-written book. But in any event, of course, you can find many instances of the Borel-Cantelli lemma all over the place. You could look on Wikipedia. Although, don't rely on it. We were burned recently by an error in Wikipedia. It seems like so there was an error on a Wikipedia page about the Wishart distribution. And then we noticed that all of these other papers that seemed to be published after the wiki page had exactly the same error. So a lot, it's probably some undergraduate statistics student, probably from Podunk University in Idaho, wrote this wiki page, and then everybody's, catching the bug in their paper. So just be a little bit leery of Wikipedia. Don't assume it's the truth of everything. So anyway, instead use Billingsley, which is the truth of everything. So okay, so any questions? That's the end of types. We're going to use the method of types to talk a little bit more about universal source coding. But this is all of the machinery we essentially need for the method of types to prove universal source coding. Yeah.
So we know that the histogram basically approximates the distribution. So how do you fit this to that common practice?
So you're talking about like actually building a code?
No, this affirmed that the fact that histograms usually approximate distributions.
Oh yeah, it does. I mean, in some sense, you can think of this as like a maximum likelihood estimate. Like if you have enough data, a histogram gives you the distribution, right? I mean, histogram will become a better and better approximator of the true distribution as you have more entries, and this sort of proves that.
So this proves basically.
Yes, among other things. I mean, like I said last time, I mean, in some sense, this is really an instance of asymptotic consistency in statistics and maximum likelihood estimation. If you like that kind of terminology, it's the same basic idea. Other questions?
What exactly do you use the Borel-Cantelli lemma for? I mean, I don't know what the lemma is, but I'm just curious why you need it.
Oh, it just gives us this statement that this event that if it's the case that you sum up an infinite number of indicators and you take its expected value, and it's value is finite. You're summing up an infinite number of indicators, but its value is finite, the expected value is finite. It means that that event must have probability 0. That's essentially what that lemma states. And we're just using it. It's just sort of adding strength. It's adding strength to this argument to say that, the typical set is really all that happens. That's the point of this slide. I'm not going to ask you to prove this Borel-Connelly lemma on a homework set, for example. But I think it's sort of an interesting point. It's an interesting other perspective. Okay, so let's talk a little bit about universal source coding. So we're going to talk about a couple of different source codes in this class. We're going to talk about Huffman and Lempel-Ziff. And my guess is you've probably seen Huffman codes before. Raise your hand if you've seen Huffman codes. All right, so we're going to look at that. But that's an instance of a Huffman code is an instance of a non-universal source code. And the reason why is because it uses the probability distribution. What a universal source code is really one that doesn't use P, doesn't use the probability. Like, let's say you have some random source, and you don't know what the probability distribution is, and you don't want to observe that source for a long time in order to get an accurate estimate of the histogram so that you can use a Huffman code. Is there any way to code for that down to the entropy? That's the idea of universal source coding, is to not have to explicitly use P of X. Now, and sometimes we've already seen this, and we've seen this in the context of the asymptotic equivalence property, but we're going to revisit this again because it's kind of a weird concept. I want to make sure everybody understands it. And that's why we're like, if you think about chapter 3 and chapter 11.1, they're kind of redundant, except that chapter 11.1 is maybe a little bit more refined because it's using types, and also it's saying the same thing, and we're visiting 11.1. In fact, I think this is actually 11.2 in the book. Does anyone have a copy of the book? Does 11.2 talk about universal source coding? Section 11.2? I think that's probably right. But in any event, let's just try to get an intuitive feel for it. It's basically saying, like, remember in the asymptotic equivalence property, all we have to do is just index large blocks, right? We just, we only need to know the typical set and have an index within the typical set, and then whenever we have a large block, we just look up which index number it is of that large block and send that index. And then the receiver, or the person who does the decompression, says, oh, that's block number 478. That corresponds to this string. So what's stored on disk is the index. And the reason why that works is because when you have a large block, the only things that occur are the typical things. And so if you only know the typical things, then you only index the typical things, then you don't need to actually know the probability. So here's the question. Do there exist codes that can compress without knowing the probability and that do so, that can compress at the entropy limit or down to the entropy limit? And so the other question is, can we compress down to the rate R? And remember, R is the rate in units of bits per symbol. So we have a source string, and we want to use a certain, on average, a certain number of bits, which are like binary string, certain number of bits per source symbol on average. That's what our rate is. And entropy is also measured in units of bits per symbol. And the question is, can we do this universal source coding idea if the rate is strictly greater than the entropy? This is Shannon's source coding theorem. And then the other question is, what happens when R is a little bit less? We sort of saw this, but we're going to view this again. We're going to formally prove this using the method of types. So the idea, again, very similar, is that we're going to, n is long enough, only the sequences that occur will be typical, and anything that doesn't occur won't be. And so if we, just by the fact that we've encountered a sequence, just by the fact that it's sitting there waiting to be compressed, means that it must be typical, if, again, the block is long enough. The problem set, there's a really nice problem set in problem set 3. It's one of my favorite, it's actually my problem that and it's actually a MATLAB problem, and I hope you guys start it now, because it's a really fun problem. And it gets into the nature of this, about sort of, like, imagine you have a 10 megapixel camera. Raise your hand if you do image processing at all. A little bit of image processing, okay. Raise your hand if you know what image processing is. Raise your hand if you have a camera. Okay. Seriously, do you have a camera? I have a couple of cameras, actually. Do you have a camera? You have a camera. So okay. Okay, so everybody's got a camera. And raise your hand if you've ever taken a picture from your camera. Now, let's say it's a 10 megapixel camera. Maybe it's less, maybe it's more. But imagine, let's say each pixel has, let's be conservative. Let's say it's 8 bits per color channel. So each big pixel has 24 bits of possible colors. So you have 10 million pixels, each with 24 bits of variation. So how many possible scenes can be represented in that 10 megapixel camera? So, well, how many bits is it? It's 2 to the 24 times 10 million. So 2 to the 240 million possible images. Now, if you lived for the entire span of the universe, and you took a picture every nanosecond, would you have used up all of those images? Not anywhere close. Not anywhere close. If you took a picture of every square micrometer of the Earth at 10 whatever it is, 10 would you be able to cover the Earth with these 10 square micrometer images at 10 megapixels? Would you use up a big lot of these sets of images of 2 to the 244 million images? No, not even close. 2 to the 240 million is astronomically big. Right? The point is, within this space of possible things that can be represented in 2 to the 240 million bits, only a tiny, tiny, tiny little sliver ever occurs. Okay. So every single compression algorithm that we use for real signals, whether it's JPEG or video compression, H.264 or whatever that, I don't know if that's a codec or if that's a inclusion package. But the point is that every single compression algorithm that we use is basically, in some sense, doing some form of typical set decoding. Now, it's not really doing typical set decoding, but it's basically making assumptions about the kinds of signals that you might have. Right? It's basically saying, okay, well, it occurred, so it must be typical, and because it's typical, I can do things about it. Like, here's an example. If you take I always do this example. If you take two random points, like point this way and then another point here where the angle is very, very similar, chances are it's going to be almost the same image. Like there's long bits of white wall here and then long bits of white wall. So if I take those two random points, I'm looking at 2 bits of leaves, or over here it's 2 bits of dirty window and building. Right? Whereas if I take 2 very, very distal points, the image of this white wall and the dirty window is very different. The point is that there's a lot of sort of spatial locality, spatial correlation in natural images. And most natural signals have that property that, if it's music, things that are close in time sound similar. If it's any sort of time signal, things that are close in time have similarity. If it's an image or if it's 3D, in 3D space, if you're looking at a neural image of the brain, things that are very, very close have sort of similarity to them. And so in some sense, everything that occurs, if it obeys that property, is typical in some sense. Things that occur, they occupy this tiny, tiny sliver of space of 2 to the 240 million possible bits of a 10 megapixel camera. So what the problem set is kind of asking you to do is create a bizarre universe where you still have very, very low entropy samples, but from our perspective, it looks random. So like our world obeys a certain set of statistical properties, our universe, and we can exploit those in compression algorithms by doing sort of typical set kinds of things, although it's not really typical set, but where the typical set is by saying, well, it happens, and so therefore we can use rules to compress something that has happened, because we assume certain properties of things that have happened. Another thing about compression algorithms is you've probably noticed that if you take a JPEG image, sometimes from the same camera, 2 different JPEG images are the same size, are different size. So ever noticed, like if you take an image in a very, very clear day, brightly lit day, the JPEG images are smaller than if you take it sort of in a foggy evening? Ever noticed that? Or in dark? Take a look at your camera. Those of you who have cameras, it sounds like everybody. Have you ever wondered why the size of the JPEG images are different? Well, because certain things are more typical, certain things obey sort of more statistical properties and are more compressible than others. I mean, there's a lot of nuance that I'm skipping over here because, of course, JPEG is lossy compression and everything, and you can sort of always decide how much you want to lose, and you can increase the size of the JPEG image. But at a given overall level of distortion, if you fix the sort of distortion that you're willing to achieve, certain images are going to have smaller sizes. They're going to compress easier at a given level of distortion than others. So the typical set is beginning to get at that idea. This is an idea that we'll encounter a number of times in this class. And what the typical set idea does, it's not a very practical compression algorithm, but it's the same basic idea. It's like the fact that it occurred must mean it's typical, and so therefore I can code for it. If the property that you're assuming is that it occurred, and anything that didn't occur is I don't care about because it will never occur, or at least it won't with any probability. So we only encode the things we see. So we'll need at most the size of the typical set code words, which we can index with NH bits. So let's formalize this in the method of types. So from the method of types, we've got to the name of NHP sequences of type P. Right? That's the bound we have. So we need NH bits, NH of P bits to represent all sequences of type P. Because there's that many. And if we're planning to code at a rate R, so remember R is our sort of rate. So like, okay, I want to code at rate R. If it is the case that R is greater than the entropy of that type, we're in great shape, right? Because we can use NR bits to represent such sequences, and we've got bits to spare, perhaps. If now, as n gets big, we prove the theorem that says only those types that are close to the Q generating distribution Q are going to occur. And now here's the key: there's an exponential number of sequences, but only a polynomial number of types. So essentially, since the only types that occur are the ones that are very close to Q, there's an exponential number of sequences, polynomial types. Essentially, only one of those types must occur. And it gets all of the probability. So one of those squares, one of those blocks in that oval have all of the probability, whichever is the one that is closest to Q. And then asymptotically, as n gets big, that becomes more and more so. So then the type that occurs is close to Q, and as long as this condition is true, as long as we're not trying to code at a rate less than Q, since Q is close to the type that occurs, we can use NR bits and everything's great. We've got enough bits to encode all of the types that occur within the type class that is close to Q. Whereas on the other hand, if R is less than the entropy of the true generating source, then we can't do that because we won't have enough bits to represent all of the possible types that occur in that type class. That's very close to Q. So does this make sense? Kind of, sort of? So we've got, this is our setup that we saw before, just restated. We've got source messages, we've got n source messages, or sorry, a length n source message. A k alphabet, there's k to the n possible messages. There's n source letters in each source message, and we want to encode it in m bits, and so there's 2 to the n possible messages. Okay, so here's the notation that the book uses, which sometimes needs a little bit of explanation. So what's called an MN code. What does that mean, MN code? So we're going to be talking about sequences of codes. And we're going to use what's called an MN code, which is a code that is for source messages of length m that have source messages of length n, lowercase n, that have m code words, or 2 to the lowercase m code words. So it's at a fixed rate. So a rate r, we're fixing the rate. The m code words, the n source symbols, and this is the idea. We've got these source symbols. These are all our source messages, right, that we could possibly have. And this sort of goes on. And we send one of them to an encoder. And what comes out is a code word, which is m possible code words. Right? And the code word is of length m. And this is binary. What we're encoding in is a binary alphabet. And the rate of the code, remember again, is log m over n. So it's log of the number of code words divided by the number of source symbols. Is anybody not clear about this? This is critical. If you don't understand this, you won't understand what comes next. We've already said this actually several lectures now. But this should be very, very clear at this point. Raise your hand if this is very, very clear.
So it's m over n, right? Lowercase m.
It's lowercase m over n, that's right. So m is 2 to the n. M is 2 to the lowercase m. We had that on a previous slide. So what is an m encode? So an m encode is one that uses m codes for n source symbols. And so it has a rate of r bits per source symbol. So here's how we define the code. So this is a fixed rate block code of rate r. So we've got a sequence of IID random variables distributed according to q, which q is unknown. We have an encoder and decoder function. So what the encoder does is it takes a sequence of length m from n from our source alphabet and spits out an integer between 1 to 2 to the nr. I said 2 to the nr, it's a rate r code, so 2 to the nr is the total number of possible messages. Right? So 2 to the nr, I mean, getting back to this thing, that's basically m, right, at the given rate that we're at. And then a decoder function takes some integers. Just like I said, we're basically representing a code word with just the integer index of that code, right? And then since we're only representing it by the integers, we need, and there's 2 to the nr possible integers, we need nr bits to store that integer on disk. And then a decoder basically takes, that integer represented as nr bits, and it says, oh, well, I want to map it back to the original source message. And then we have a probability of error, which is the probability of this event. So this is, it's based on the source distribution, so it's Q. The probability comes from some underlying source distribution. And it's the event of all sequences X, such that when we encode X here, and then we decode it, we don't get back the original. Probability of error. The other thing to note is that, MN really designates a series in N of codes. So like the kind of theorems we're going to be proving is things like there exists a series of MN codes that approach probability 0 of error as long as the rate is greater than the entropy. We're not going to say for given n we can do it. We're going to say it's an asymptotic argument. We're saying that when n gets big enough, we can make our rate as close as we want to the entropy. And if we want to do better, we might need to make n even bigger, but we can eventually do it. That's all that the theorems are going to say. It's not going to say for a given fixed n, suppose you say, well, I can only do n of 32, or I can only do n of 68. You might not be able to come very close to the entropy. But what the theorem is going to say is that, well, sorry, you can't do it then, but if you make n big enough, you can. No matter how close to the entropy you want, as long as you're bigger than the entropy in terms of your rate. So does that make sense? I hope. If it doesn't, you can watch it on YouTube again. Along with, I heard Sai's got a new video out. Anyone seen it? Does anyone know who Sai is? Oh. Context switch.
I thought he was in 27.
Oh, maybe that's true. In fact, to be honest, I just made that up about him having a new video. Like I said, I never promised everything I said would be true. But I think you can assume that the things they say about information theory is true. But don't assume if I say anything else, like these random stories I tell you, don't assume they're true. They could be just complete fabrications. In fact, this particular thing I'm telling you right now about things I'm telling you might be a complete fabrication, might itself be a complete fabrication, which would mean that everything I'm telling you is true, which of course would be a paradox. So I never said I won't give you paradoxes. Okay, maybe what we should do is take a break. Let's take a short break, and hopefully these ideas will digest a little bit, and then we'll come back. Okay, so after the break, so here's our definition of a universal. Now, universal in the same sense we talked before. A universal rate R block code. So let's talk about what this means. First of all, it's universal. It's rate R, which means that it encodes at a rate of R bits per source level, or source letter. We've got an encoder function F and the decoder function phi. And it does not it doesn't directly depend on the source distribution Q. And also it has to be the case that the probability of error goes to 0 as n goes to infinity whenever the rate is strictly above the entropy. Okay, so the error going to 0 is part of the definition. So this means that, in some sense we require the ability to code at that rate. And which essentially really means we can code without error, because we can make that probability of error as small as we want. So we can make it as small, and especially since we're going to see that these errors are going down exponentially, we can make it as small to, for all intents and purposes, essentially be 0. Without, again, referring specifically to the distribution. So let's see how this can be done. So in doing this, we're going to prove Shannon's main theorem using the method of type. So if R is greater than the entropy, then there exists a sequence of codes with the error becoming vanishingly small. And if R is strictly less than the entropy, then the error is going to go to 1 very quickly. So entropy, like I said, is this sort of phase transition, this critical point. So here's Shannon's source coding theorem. There exists a sequence of mn codes, and we're using 2 to the nr for m, so 2 to the nrn codes. In fact, they're universal source codes with probability going to 0 for all source distributions Q that are not greater than the rate, that whose entropies are not greater than the rate. So let's see how we can do this. So we're going to fix R, which is greater than Q strictly, and we're going to come up with sort of like a local R for the current n. It's going to be a value Rn, which is going to get closer and closer and closer to R as n gets bigger. So this might be R1, R2, R3, and then here's R. So it's always a little bit less than R. The other thing we're assuming is that h of q is somewhere here. All right, so we're saying that h of q and r, we're saying that this distance is strictly positive between r and h of q, which is this bit here. Okay? Oops. Now, we're going to define a set of sequences whose type has entropy less than Rn. So this is again a function of n. So it's A of n, which are all of those sequences whose type is less than Rn, where again it's a function of n. So another way of looking at it is like the union of all types, or the union of all type classes whose type is less than R of n, less than or equal to R of n. Where R is sort of our local rate. So then what do we have? Let's see how big this sequence is. So the size of A of n is equal to the sum over all types whose entropy is less than R of n of the type class. And I guess I'm missing a parenthesis here, so this should be actually it should be this, right? And that's upper bounded by using the upper bound on the size of the type class to the negative nh of the type. We can further upper bound this by saying, well, we're again only assuming types whose entropy is less than or equal to Rn, so we can substitute the entropy for Rn. That makes it a little bit bigger. And now again we just forget about all of the constraints on the types and we just have this polynomial bound, upper bound on the number of types, n plus 1 to the x. And then we write it in the same way that we wrote it before. So notice, except that in this case, it's an Rn is involved here in terms of the current rate. And the other thing to remember is that how do we get Rn is what we subtracted off the size of x log n plus 1 over n. And so that means we get 2 to the n to the nr. That's our bound. Just by the definition of Rn. So an, this thing is no bigger than 2 to the nr, which is the rate. So therefore we can index an with nr bits, and we do this, right? So here's our encoding function. We say the encoding function takes a sequence, and if it's a member of A sub n, then we just take its lexicographic index inside of this set, right? So the lexicographic index is an integer between 1 and to the nr, right? Lexicographic just basically means we sort them, all the guys in an. And otherwise, if it's not in an, we just send the message, we compress it to the integer 0, which obviously is going to be wrong, but that's okay, because with the error, that's going to be an error that's not going to. Now the one thing to note is that this encoder doesn't depend on the source distribution, only on the encoding on the set A of n and on R of n, right? Because what did we use? It's basically, we have some rate, we have the sequences, and we can compute their empirical distribution, their empirical type. We can compute the entropy of the empirical type. Right, so this is all done in some sense beforehand, right? We just have this, we can compute all sequences whose type, and we compute the entropy of the type, and stick them in this set an. We haven't even touched P, we haven't touched Q of x. So I should say, and of course A of n. Oops. So an error occurs if the sequence is not in A of n. And so let's actually look at this. So we can represent, let's look at the probability simplex to indicate which types may be encoded. So here's an example. When the alphabet size is 3, we can have, we're sort of in a 3-dimensional space, and the probability simplex corresponds to this triangle. Right? So all of the points within this triangle correspond to a valid probability distribution over 3 symbols, right? So this is called the 3-dimensional probability simplex, or maybe 2-dimensional probability simplex. But the point is, it's a 2-dimensional triangle within a 3-dimensional space. But you can do this in n dimensions as well, right? So when you have an n-dimensional probability distribution, that can live in an n plus 1 dimensional space, right? Or actually, it can live in an n-dimensional space and it actually has an n minus 1 dimensional triangle, or n minus 1 dimensional simplex. And here's essentially that triangle again for the alphabet size is equal to 3. And we know that the highest entropy point in that triangle is the one where it's 1/3, 1/3, 1/3. And that's the point that lives right in the middle here, right? It's 1/3, 1/3, 1/3. And then the low entropy ones are the vertices, the extreme points of the simplex. Those guys each have entropy 0. And as you move from entropy 0 to here, you're increasing the entropy, right? What does this point have here in the middle? Sorry? 1. That's right. Entropy 1. This is entropy 1. This is entropy 1. This is entropy log of 3. There you go. We've got it. Okay, so there's the simplex. And basically each point is a type, and the points with rational values and live inside of the simplex are types, really. And they're, numerators, values between 0 and n, and denominator n. And the yellow region corresponds to those types that have relatively low entropy, and they can be encoded correctly, assuming that R, what the rate does, that R of n sort of defines this ball around high entropy. And then it's basically saying everything outside of the ball has low entropy, and so therefore those types that live in the yellow region can be encoded accurately because the rate's greater than those entropies, whereas the stuff inside of the blue region has got too high an entropy. It's entropy greater than R of n, so it won't be possible to encode. And of course, right on the circle, right on the boundaries, are those types, if there are any, that have entropy exactly equal to the rate, the current rate. Does everybody get this picture? Okay, so what we're going to do then is upper bound the probability of error and shows it goes to 0 as n goes to infinity, when the rate is greater than the entropy. So an error occurs when the sequence is not in our set, so the probability of error is 1 minus the probability of the set. So it's basically summing over all types whose entropy is greater than Rn. Okay. And we can upper bound this by taking the polynomial upper bound on the number of types, which we've done now a lot of times. So this should be not unfamiliar to you. And then we just here, what we're doing is rather than summing, we're just taking the max. Okay. So that's certainly upper bound. So everybody has the same in the sum. And let's take what we're doing is we're putting the max inside of the exponent and saying this is 2 to the that thing. And so what ends up happening is that we end up getting, so this is all, well, let's assume this, you can see this one now. First of all, the constraint on the min is the same as the constraint on the max, right? We're using our upper bound on Q, and then this is the extension. It's Q of the type, remember, was 2 to the negative n p of nq, so we're using that upper bound, and then putting 2 to the negative that thing. So we're using that bound, and then except rather than taking the max, it becomes the min when it's inside of the exponent. So the max of a bunch of stuff, of something that's an exponential, becomes the min of something inside when it's the negative of the min. I'm not saying that very well, but hopefully this should make sense. It's 2 steps. We're using the bound on Q of T of P, and then secondly putting the max up in the exponential where it becomes a min. So what we have is the following. We have this series of rates for n. The rate is increasing. These rates are increasing, and they're asymptoting in R. We have that R of n is less than R for all of n, and we have that H of Q is less than R. So here's sort of our situation we're in. We have H of Q down here. We have R up here. We have this constraint here. We're only summing over P such that H of P is greater than R of n. Here's R of n here. So we're only summing over those types where the entropy is greater than R of n. Whereas Rn is increasing, it's going up to R. Yet H of Q is down there. So at some point what's going to happen, since we know that this R here is greater than H of Q. That's what I said before. So we know that eventually R of n is eventually going to surpass H of Q. So eventually this is going to be quantity, this quantity here is going to be positive. Okay. Here's the picture again. And we're choosing only P, only summing over those terms where the entropy of P is greater than R of n. So therefore what we have is that the entropy of P for all guys in the sum is strictly greater than R of n, because we're doing that, and that's eventually going to be greater than h of q, because of the assumption, because we said that R is strictly greater than h of q. So with this thing, we can say that P is therefore not equal to Q, because this inequality wouldn't be true unless this was true. And so therefore that means that the dpq is greater than 0 for all of those p's that we're summing over, which basically means that this whole thing, this probability of error, is upper bounded by this, where the first factor is a polynomial in n, and the second factor is 2 to the negative n of what? Even though we're taking the min over all p, such that h of p is greater than R of n, that whole thing is going to be non-zero. So that means that it's going to be 2 to the negative n of something which is positive, and so therefore it's going to be a decreasing exponential as n goes to infinity. Which implies that the probability of error goes to 0. Okay, so that's sort of a picture of what's going on. It's a little bit of a complicated proof, but I think that if this doesn't make sense in class, I mean, if you read the book and try to go through the proof, this I believe it or not explains it much more clearly, I think. But thanks to the use of these pictures. But this is sort of a way to describe it. So then conversely, we have the converse of the theorem. And I'm not going to go through a lot of the steps because I think the intuition is more. But basically, it's saying that if the rate is less than the entropy, then the error has to go to 1. It's very easy to set it up. Maybe I'll ask you as a problem. So stepping back a bit, we're basically saying that the entropy, since the entropy is sort of this limit of compression, it's sort of a good way of measuring the information. You know, getting back to lecture 1 even, it's a good way of measuring the information that exists in a source. It doesn't make sense to you to say that here's a source. How much information is in that source? Well, it's the number of bits of the best possible compression you can do. That's sort of the fundamental quantity of stuff that's in that source. And maybe you're using way too many bits to express it. You know, some people who talk a lot, for example, maybe they're using way too many words to express the underlying message in what they're saying. Yet other people who don't say anything, there's a distortion because you can't get their meaning because they don't explain things using enough words. Both things go both ways. And the entropy then is sort of that point at which if you go below, you're going to have some distortion. You're going to have some error. So this explains why you can't run gzip on gzip on gzip. This explains the problem. Okay. Any questions about this? Okay, so actually, let me ask this question. So once a source is compressed down to its entropy limit, what does that source look like? Yeah, uniform. So what else?
Like images of like white lines.
Yeah, well, it's uniform and independent. It's IID uniform. So the critical thing is that if you look at a sequence of bits that corresponds to an optimally compressed source, no matter what that source is, if it's compressed down to its entropy, it's going to be sort of the perfect uniformly at random, independent IID fair coin flips. So one way of getting a great random number generator is take a large chunk of stuff, running gzip on it, and then just sequence through that file, asking for random bits. Of course, you can only do that once, because if you do it again, then it's no longer random. Then there's a cyclicity. You can only do that once. But if you only need a small number of random bits, and you're only going to use them once in your entire life or in the history of the universe, you can do that. And now, why is it that it must look like a sequence of uniformly random independent bits? Good.
And you could, if it were not, then you could compress it again.
That's right. Exactly, exactly. If it was not uniformly random independent, then you can compress it further, which would violate Shannon's theorem. So then, what if we, here's another question for you. Suppose someone gives you true sequence of truly uniformly at random bits, and then gives you another sequence which is gzip run on pictures of your vacation, or it's not really gzip wouldn't do it, but some perfect compression of some photos. And so let's say that the true uniformly random bits is the same length. How would you tell the difference? What's the difference? They're both uniformly at random, true random bits, right?
See which one uncompresses. Photos on vacation.
Well, yeah. I mean, is there any way of doing that without uncompressing it? No. I mean, that's exactly right. I mean, you're right. In some sense, the code is the key. It's the decoder. It's not just any sequence of random bits. Sure, it's a sequence of random bits, but it's a code word into some decoder, and the decoder is the thing that maps from this code word, the sequence of random bits, back to, it's an index in some sense. Your compressed bits is really an index into a table which is sort of implemented by the decoder. Now the decoder is more than usually just a big table lookup, right? Usually effectively it's sort of like an algorithmic table lookup. That's what decoders are really doing. I know it sounds bizarre, but it's kind of what's going on. So the decoder is the key. And if you took any arbitrary sequence of random bits and you looked it up in your table, it wouldn't be the source. It wouldn't be the right image source. Okay, so that's universal source coding. Are there any other questions?
How often does it make sense to? I mean, you take random bits and then you decode it. How often does that make sense? I guess it's semantic. But...
I mean, to take real random bits.
Yes.
Well, that doesn't make sense at all. That's what I'm saying, though. Is like, on the one hand, I'm saying that if you compress something perfectly and you look at it, for all intents and purposes, it will be uniformly at random bits. However, if you take a true sequence of random bits, it would also, for all intents and purposes, look like random bits. And there's really no way of distinguishing between them.
No, I mean, say you compress an image and then you get like a bunch of random bits, but now you generate these random bits and then you decompress that image. And would that tell us something more about the statistical properties of the world?
It's hard to know what precisely that means, because it's to say more than what. I mean, what I'm saying is that the decoder captures the statistical properties of the world in some sense, right? The decoder is the thing that basically takes the random bits, which is kind of like an index, and sort of imparts, based on that random bits, structure back. Imparts redundancy, which namely makes it a real image that we would likely see. So it's the decoder that in some sense represents the structure in the world, not the random bits. The random bits is really just an index. And because it's random, it's an efficient index. It means that you're likely to use all of them at that length.
But does that necessarily mean that everything in your typical set is typical? Now, this is kind of semantic, because I mean, if you take random bits and then you bring it back, I mean, would that appear natural to us, or would that appear to some random noise?
Well, let's say, for example, that you do perfect compression. And you compress it down, epsilon close to the entropy rate, and so you have to the NR messages, and let's say that every one of those messages might possibly happen. in that compressed sequence, any statistical test will say in that compressed source, they'll say, well, this is random. I don't find any structure. I don't find any dependency there. If you then took a real random bit string, you would get back a message. You'd just get back the wrong one. You would just get back, rather than a picture of say, a tree, you get a picture of a banana or a car or something else. If they're all possible things. Now, in real life, I mean, things that we haven't really talked about real compression algorithms yet, because typical set decoding and typical set compression is not JPEG. I'm making an analogy between typical set decoding and JPEG because some of the concepts are the same. In the sense that which is occur, that which might occur is that which is got a code word, and that which won't occur isn't. JPEG is the same way. I mean, if you compress, and JPEG is also different because there's a distortion component. But if you were to take, in fact, maybe you should do this for your problem set. Like when you have an image of random dots, try compressing it in JPEG and decompressing it. You see all the distortion. There's a lot of distortion. When it's truly uniformly at random dots, JPEG does a terrible job because it's not what it expects to see. Now, in the case of typical set decoding, if you give it an atypical sequence, it gets an error. In the case of JPEG, you get distortion. Right? I mean, but that's kind of the same thing. When we start talking about rate distortion, we start looking at the trade-offs between the rate of a code and how much distortion. So you can actually make the rate lower than the entropy, but you'll get an error. And the question is, how do you guide that error? How do you make the distortion nice in some way? You will get distortion. And the idea about JPEG is that they try to make the distortion such that we don't notice it that badly. Humans don't. That's the whole idea. But more distortion means bigger error. And so it's very similar, because when you give it a random dot pattern, that's not a typical set for JPEG. And the consequence, it's not like it says, sorry, I can't compress this. I mean, JPEG has to compress everything, or at least has to do something with everything. It just will look terrible when it comes back out. It won't look like the same random bits. I don't know, maybe it won't look terrible. Maybe it'll look even better. Who knows? It'll look less artificial, maybe. Okay, we're going to start talking a little bit about stochastic processes. And I think some of this stuff is kind of review, so I'm going to go over this very, very quickly because I wanted to get to the entropy rate. So far, I mean, we've been basically talking about, this is now getting into chapter 4, which we should start reading. I think I mentioned this on the Canvas thing. But basically, I mean, all of the sources we've talked about so far are IID. And each symbol that comes in, on average, gives you entropy number of bits per source symbol, right? That's sort of the compression. If you compress it down to the entropy rate, then each one of these source letters is giving you an additional entropy number of bits, at least. But what happens if there's dependency? What if it's a stochastic process, so it's not on a sequence of IID things? Is there a notion of entropy? So what is a stochastic process? What does it even mean to talk about the entropy of a process? And there's a nice, well-defined notion. So just quickly, let's review a couple of concepts. And if these aren't familiar with you, you should review them either on the slides or in some books. But basically, we have the notion of strict sense stationary. Stationary basically means that if you've got a stochastic process, which is a sequence of random variables that are not necessarily IID or independent or anything, it basically means if they're stationary that you can do time shifts and you get the same probability distribution. That's the notion of strict sense stationarity. There's the notion of a Markov process, which basically says if you look at the conditional probability of the n plus first symbol, conditioned on all previous ones, that's the same as conditional probability of the n plus first symbol given the previous one. In fact, that's a first order Markov process. So it's a conditional independent statement. So it means, that later statement means that when you look at the probability of the sequence, you can write it as the product of the conditionals. Probability of x1, probability of x2 given x1, and so on and so forth. There's the notion of time homogeneity, or sometimes just homogeneous. And that basically means that the parameters or of the governing dynamics doesn't change with time. So that the probability distributions themselves are not a function of time. The only thing that changes the probability is when you change the random variable values. And so this says basically that the probability of the n plus first guy being B given the nth guy being A is the same as the second one being B and the first one being A for all A and that's for any n. The key thing is that this is true for all A, B, and n. And so another, a way of doing this is that if it's a first order Markov process and you have a fixed transition matrix, so the transition matrix is the same. The probability of going to the next symbol and given the current symbol. You can write this in this as a graph. Can people see this? Here's the graph. It's not meant to be crossed out. It's just meant to. The notion of irreducibility, which basically says that if you think about this Markov chain, this is a first order Markov chain again, and if you're at a given state, as long as it's possible to get to any other state at some point. So basically in the transition matrix means that there's a directed path from every node to every other node. So there has to be some way of getting from everywhere to everywhere. That's called the irreducible chain. And we can also define the probability of going from one state to the next state using the following quantity. You can really see this? This is viewable to you? And it's kind of hard. Okay, let's see if I can move this up a little bit. Is that a little bit better? It's the probability of x plus 1 given this stuff. And the notion of a stationary, first order Markov process that's stationary is this. Let me just go through this quickly. The notion of periodicity, and the periodic change is the greatest common divisor of all integers whose self-return probability is greater than 0. PII is the self-return probability in n steps. So it's the probability of starting in state I, getting back to state I after n steps, and that being greater than 0, and all n such that that's possible, that's the period of state I. So here's a stochastic process, first order Markov chain with two states. The station, maybe I should, if this is unviewable, I'm starting to see some, it's really a pity to close the window when it's so nice and sunny. How's that? It's not so bad. Okay, so if mu is a stationary distribution, we must have mu transpose p is equal to mu transpose, where p is the transition matrix. And in this particular case, this expression is the stationary distribution. And you can verify that very readily. I always recommend, and we don't use this book in this department, but my favorite book on random processes is Grimmett and Sturzacher. Still, it's from the 90s, but it's a great book. Has anyone seen this book before? So I think this is the best book. If I were to teach stochastic processes, I'd want to use this book. So it's really, really complete and well written. Okay, so the notion of a stationary stochastic process is that it's different than time inhomogeneous, right? A homogeneous Markov chain basically says that the transition matrix doesn't change from time to time. It doesn't mean that the probability of a given state is the same from time to time. Stationarity of a Markov chain means that the probability of a given state doesn't change from time to time. Another notion about a Markov process is that the future and past are independent given the present. So in other words, the immediate past is sufficient to render the distant past irrelevant. Homogeneous basically says the parameters of Markov don't change. And again, it's important to realize that this is distinct from this. This is not the same thing. People get that confused a lot, but they're really different. The notion of irreducibility is a directed path from all states to all other states. And the periodicity, it's the return time, the GCD of the return times for each state. Each state has its own period. So it turns out now stochastic processes have entropy rates, interestingly enough. And what do you think the entropy rate of stochastic process might be?
Be less because it goes to the
Well, I mean, it just before you even say it's less than or greater than, what might that mean? Does it have? I mean, given what we know, can we come up with a?
Average number of bits per symbol.
Right, it's the same thing. It's like the number of bits provided per symbol. But do we have the machinery to actually define such a thing? Well, it turns out we do. Okay. We can define it in this way, which says, okay, let's say we've got a stochastic process. We can define it, assuming this exists, it's basically just the limit as n goes to infinity of the entropy divided by n. Right? Like if this is independent, this is exactly, we get back the entropy. And the limit doesn't matter. The n cancels out because if it's independent, this sums over n random variables, the n cancels out, the limit vanishes. So this seems like maybe a reasonable generalization. So therefore, it's again like the per symbol entropy given by the stochastic process when n gets large. Here's the example when it's independent. So it's the entropy of any one of them. And which makes sense. Any one of them is the same because it's IID. That wouldn't make sense if it's not IID. So what about when it's independent but not identically distributed? Does this exist? Does this limit exist necessarily? Does a lim sup exist? Like what if the entropy is sinusoidal? Well, positive, non-negative and sinusoidal. It's going like this. So we're dividing by n. Does that limit exist? No. Is there a lim sup?
Yeah.
Yes. So there's a lim sup, but the limit doesn't necessarily exist. Here's another example where it doesn't exist. So it's independent, but we're saying that the probability of 1 is 0.5 when this condition is true, and the probability of 0 when this condition is true. And I guess the idea is that these intervals, where it's 0.5 and 0, are sort of getting bigger and bigger as n gets bigger and bigger. Or something like that. So such a limit doesn't exist in that case. Now how about this? This is an alternative definition of the entropy rate. And here what we're saying is, well, let's take the conditional entropy. It's just basically saying, okay, well, now I'm conditioning on the history all the way back to the beginning of time, which is time 1. And I'm saying, here's the conditional entropy. So again, if everything is independent, what is this equal to? If everything's IID, so if this is this is independent, then does any of this stuff matter?
No.
No. So that if it's independent, then all this stuff is gone, and we just get h of x1 again if it's IID. But of course, it's not going to be IID. But still, this is something that could be seen as a reasonable definition of the entropy rate of the stochastic process. How much new information am I getting at every time step over and above what we have already received? I mean new bits that we're getting. I mean, if it's completely redundant, if I keep repeating the same number 4, I'm not getting any new bits. Or if I keep doing a number which is a deterministic function of my history, like people who repeat themselves,
So does that mean that all pseudo-random
All pseudo-random number generators have zero entropy. That's true. They shouldn't, but they do. They don't act like they do, but they do. I mean, once you know the generative process, that's actually one of the problems, is that it's just extraordinarily complicated to figure out what that determinism is. And cryptographic applications rely on the extraordinarily complicatedness of figuring out what that determinism is. But if you don't, and if you just treat it as random, it sort of it appears like it's random, but it's really not. So they call it pseudo-random. So the first little theorem we have is that this conditional distribution, is decreasing in n and has a limit. Now this is not, it's not to say, just don't get this confused with, it's not saying that conditioning reduces entropy. Because remember, every time we increase n, we have more things on the right-hand side of the vertical bar, but it's a new random variable. Right? So it's h of n plus 1, h of n plus 2, h of n plus 3. And we've never, so what we need to do is we're saying that quantity, this conditional entropy as a function of n, is itself decreasing. And to prove that, however, it uses that idea. So we start with h of x of n plus 1 given the first n variables. Then we use conditioning reduces entropy. We get rid of x1, and this increases it. But then, how do we get this next line? How do we get this equality?
You move it, and then the probability distribution is the same. Or you shift it to the left.
And why can we do that?
Because it's stationary.
Yeah, exactly. Stationary. So therefore we can shift things to the left and right. We get the same conditional entropy. So therefore it's a decreasing sequence, or non-increasing sequence. Is there a difference between decreasing and non-increasing?
Well, you can be flat.
Yeah, it can be flat. So I always try to say non-increasing. Okay, so what have we got? So we've got this definition. Oh, actually, I think that's just the final bit. Okay. So something else we're going to use is something called the Cesaro mean. We're not going to prove this, but this is somewhat intuitive. It's basically saying that, let's say that you've got a sequence A of n, and it converges in n to A. And then B of n is just the mean of the first n guys of them. Then B of n is going to converge to A2. And the reason why is because if A of n converges to A, at some point or another, B of n is going to be averaging together so many guys that are so close to A, B of n might as well also converge to A. All of the guys in B of n that are not close to A are going to cancel out at some point because of the 1 over n. That's sort of the friendly party description of this theorem. It's always good to anthropomorphize, to turn theorems and numbers into people, because then you become familiar and friendly with them. And so here's the idea. Then this gives us the next theorem. So what the next theorem states is the following, which is that this notion of entropy rate, which is taking the limit if n goes to infinity of 1 of n over the joint entropy, is the same as this notion of entropy rate, which is the limit of the conditional entropy. And that those guys are the same. And so it's a simple proof using the Cesaro mean. We basically define B of n in this way. Here. And that then is used, we use the notion of conditional entropy, the chain rule of entropy to get this part. And then that conditional guy becomes A of I, right? So A of n converges to H prime, which is in 7.36, right? And B of n converges to H prime because it's the same thing. But then, by definition, B of n converges to H. So therefore, they have to be converging to the same value, thanks to the Cesaro mean. property. And again, just to remind everybody, we're assuming it's stationary. So, you know, for a stationary ergodic process, by the way, the ergodicity is a fairly sophisticated concept, but roughly speaking, it basically means that time and ensemble averages are the same. So it means that, for example, that this quantity, 1 over n, of the probability of any given sample also converges to the entropy. And that's also something we saw with the typical set theory. So for stationary ergodic processes, this is also going to be true, even if it's the case that it's not independent, as long as it's stationary ergodic. And so thanks to this property, we can prove AEP or typical set-like theorems to show source coding for stochastic processes, stationary stochastic processes. But this is done in section 16.8 of our book. It's the Shannon-Macmillan-Bryman theorem. It's the generalized AEP. And we're not going to cover that in class because there's a lot more stuff to cover before we get to that. But suffice it to know that it's not necessary to assume that our sources are IID. So when the entropy rate is, in fact, stationary Markov chain, now this is like a first order Markov chain again, the entropy rate is particularly nice because we start with h of x, which is h prime of x, which is equal to this limit, and we know it's the same. But now, thanks to this theorem that we have, we can look at it in both ways. And since it's a first order Markov chain, the only thing that matters is the random variable at the previous time. So everything, x of n is conditionally independent of everything before it given x of n minus 1. So we take this limit, but thanks to the stationary condition, this is just the conditional entropy of x2 given x1. So this becomes the entropy rate. This is the number of bits in a stationary first order Markov chain. The number of bits we're getting is the conditional entropy. The number of bits we're getting on average per source symbol is the conditional entropy. And here's the actual representation of it. Mu I is the stationary, or mu is the stationary distribution, and Pij is the transition matrix. So that is the information per source symbol of a stationary first order Markov chain. Doesn't look too bad, does it?
This looks like is this in some way related to the observability? Linear.
I'm sorry. Can you say that again?
Is this somehow related to the observability of linear dynamics?
I'm not sure. I'm not sure exactly what you mean. What do you mean by the observability of linear dynamics?
So this seems to imply that after you know a bunch of states, then you can after you observe a number of random variables, then you can effectively have something with the state.
We're talking about offline. Or come to office hours. Come to office hours, or come to the Canvas discussion section. Please, let's try it out. Or Skype me. You can Skype. I'm available by Skype. Well, though we should set up a separate meeting. But I'm usually working in the evenings anyway, so if you've got a desperate question you want to ask me. I want to be available to everybody, so I mean, I know sometimes people, I mean, but then on the other hand, maybe you don't want to be available to me, so. But it's at least one directional open door. Okay, let's do a couple of more examples. Actually, we're running out of time here. Are we going to finish this today? No, this is going to be too long. So let's I think we should end with that. There's the end. And are there any other lingering questions? So we're going to get into a little bit more mechanics of this in terms of where we're going with this, and then we're going to start talking about some coding strategies, source coding. And it's going to be mostly like we're going to talk a lot about Huffman, and we're going to see how Huffman is optimal, Kraft's inequality. That's also pretty critical. So there's some fun stuff coming up, but and some things that might even be useful.
Is there a strong theory for what happens if you have error in estimating the probability distribution?
Yes, there is. And it's the penalty you'll get, as we will see. And in fact, in some sense, we already saw, is the Kollek-Raman divergence. So if we assume the distribution is P and the distribution is actually Q, then what we're going to get, our compression rate at best is going to be the entropy of Q plus the Kollek-Raman divergence of P and Q.
So basically, you never want to assume that something's impossible if that happens. If something you thought was impossible happens, it'll really mess you up.
That could, Yeah, I mean, if something happens and you have zero probability for it, you're in trouble. Then you use an infinite number of bits. So, okay, now that's of course not really true. We'll talk about that though. Any other questions? Okay, I will see you on Tuesday. Have a good weekend and enjoy the homework.